welcome to another iteration of the Malga seminar series. I would take this opportunity to welcome our guest speaker, Davide Moltisanti. Davide obtained his PhD last year from University of Bristol. He is currently a research fellow at Nanyang Technical University in Singapore. I hope I pronounced that correctly. He has been working on action recognition and video understanding, and his talk today is about labeling actions in videos. I would let Davide introduce the topic directly. Over to you, Davide.
Thank you very much, Gorby, and thank you also for inviting me. It's a pleasure to me. So in this talk, I will give an overview of the work I've been carried out. Well, I carried out during my PhD at the University of Bristol, where I worked with Dima Daman. And as Gorby mentioned, I now at NTU in Singapore, and I'm working with Chen Change Lloyd, and still on weekly supervised approaches for video understanding. Feel free to interrupt me and ask me any questions at any time during the talk. Okay, so the area of research of this talk is action recognition in videos, of course. That is a task of classifying a given video segment into a predefined class. The talk specifically focuses on how we label the videos and how the way we label the videos affects the way models learn from the videos. So we will also see how we can move from full to weak temporal supervision to try to find a good compromise between the effort that it takes to label videos, which can be quite painful, and classification performance. Okay, so when we annotate actions, we mainly perform two tasks. First, we choose a class label. That is some sort of text that describes the action contained in the video, like crack egg. This is typically a combination of verb and nouns. And this introduces the first question of the talk, which is, do different people label the same action with different verbs and nouns? And the second task that we undertake to label actions is that we have to decide when the action starts and ends in the video. That is, we delimit the temporal bounds of the action. And this introduces the second question, which is, do different people recognize the start and the end time of an action in different ways? As you probably have guessed, the answer to both questions is yes. And we will also see what is a good compromise between the effort that it takes to annotate videos and actions and the performance that we can get from the labels. Right, let's start with the first of such questions. So in this figure here, we can see, we see two actions. The first one on the top is pull draw, and the second one at the bottom is push draw. We can notice that both actions can be described with the label open, right? Which one is the best one? Well, there is no right answer because all of these labels are valid, right? And under such circumstances, typical classifiers struggle because it is much harder for them to learn decision boundaries when there is no semantic separation between the samples. We could disambiguate by attaching a noun to the video clip. For example, we could say open draw or open door. But the focus of this work was to try to learn to train a classifier without using nouns, because we wanted to say investigate how we can learn actions in such ambiguous, semantically ambiguous setting. Okay, so the first thing we did for this work was we asked different people to watch a series of videos, of untrained videos, and we asked them to simply label each observed action in these videos. The videos were those of our our simple small egocentric dataset, the BOE dataset, and we did not instruct the annotators as to recognize the start and the end time, nor did we tell them how they should have described the action. We just told them, watch the videos, label them, and using any verb they saw fit. And this gave basically created a large variety of verbs for the same actions. For example, the action of washing a mug was labeled as wash, rinse, or wash up. And again, all of these labels are correct. So the core of the method was to build a graph where each node is a video clip. And each video clip or each node is represented with some features. Now, because this work is quite old now, in this work we used both handcrafted features like improved end trajectories, which were still quite competitive at the time with deep learning models. And we also evaluated what was the state of the art on image length at the time, as it was CNN was the state of the art, and that was overfit. And both features were encoded with value rows or Fisher vectors. So once we have the video clips encoded, we create a graph and we link them. We link the nodes with two different kind of edges. One is a visual edge, which measures the difference between the visual representation of two different video clips, and a semantic edge. Here we tried three different kinds of semantic edges. One is the simplest one, AM. We connect two nodes only if their verb labels are exactly the same. And this is what we are showing here in this figure. Like turn on and turn on and press are both connected with a semantic edge. The second type of semantic edge was AS, which links two nodes if the two verbs are synonyms. And finally, the more complex one was AH, which is we link two edges if they are related by hyponymy. So a verb is a hyponym of another verb if this verb conveys a more specific action, sorry, a more specific meaning of the other. For example, rinse is a hyponym wash. So once we created this graph, at test time, we have an unknown video clip, which of course is encoded with some video features. And we want to embed this clip into the graph. So the way we do this, we first find the nearest neighbors based only on the visual appearance. And then from these neighbors, we perform a Markov walk of two steps. The first step is illustrated like this, and then the second step like this. So as we perform this work, we visit different nodes and we accumulate the cluster probabilities of the nodes we have visited based on the weights of the edges, okay? And then we can basically assign X, the class label that exhibited the highest probability during the walk. So here is a visual example of how this works. X is the unknown video. In red, we can see the nearest neighbors. For this, for X, the ground truth action was the green one set down. So you can see that the nearest neighbors were incorrect for X. So what I can hear my voice. Maybe there are questions. Okay. Sorry. So we compared our method, which we nicknamed Sembit, with an SVM classifier, which in this case got the wrong class, which was checked for SVM, and also a KNN classifier, which also got the
We lost the speaker.
Yeah, on my side too.
Okay.
Yeah.
Okay. Maybe some connection issue.
Sorry about that. Hopefully it won't crash again. I think again it was just the Wi-Fi went down. Okay, so so here we are showing how the method performs compared to an SVM and a KNN classifier. For the SVM class, the SVM classifier predicted the wrong class. The KNN classifier predicts also the wrong class because, as I said earlier, I hope you I hope you could hear that before. The nearest neighbors for X are incorrect, as in they don't belong to the right class. However, our assembled method, because it can reach other nodes thanks to the map, are not connected just by a visual relationship, but also by a semantic relationship, then we could reach the right class, which is set down the green circles. So after this work, I stopped working on semantic and vision, and I took another path. However, if you are interested in this topic, I highly recommend checking out Mike's work. Mike was first author of this work with me, and he continued working on semantics throughout his PhD and also during his current postdoc. All right, so let's move to the second part of the talk, which is the main question is, do different people label the same action in different ways temporally? And the answer I'm going to anticipate is yes. In fact, we have seen this figure already. We saw that when multiple people are asked to label the same action in a video, they don't only label the action with different verb and nouns, but also with different start and end time that we can see here with the horizontal bar. So this was quite an unexplored territory, I would say, back then, because usually we take action boundaries for granted. We don't question the way they're labeled. We don't question if they are wrong or right. We just take them as they are, and this we will see might be an issue depending on the kind of videos we work on. So the first thing we did was we evaluated how much annotators disagree. And again, we took the annotations we obtained for the previous work, and we compared the IOU between all the different segments that the annotators provided for a number of actions in a video. For this figure, I'm going to show annotations that were connected for 10 people. As you can see, here I'm showing the IOU between all the possible pairs of action segments. As you can see, the IOU varies significantly. That means that there is quite a large disagreement amongst annotators. We also tried.
Sorry, Davide, to interrupt you, but I have a doubt since before. Maybe you said it. Are the annotators free to choose their own verb and noun? So is there any possibility that they go for synonyms or equivalent concepts, or do you give them some lists or possibilities?
So that's a good question, thanks. So for the previous work, they could use any verb they wanted. For this work, we fixed the semantic part of it. So we clustered the segments based on the class. So we have only one kind of class. So we have pickup, cap, turned up, etc. But we evaluate all the different temporal segments. Does that answer your question?
Yeah. Thank you.
Okay, thank you. So as you can see, the disagreement amongst annotators is quite high. We also tried on Amazon Mechanical Turk, or AMT, which is Amazon's crowdsourcing platform to get some work done online, and we also see that this happens when we consider a larger pool of annotators. So for these actions, WashCap and ScanCard, we gather annotation from 100 people. And of course, the IOU also varies a lot for these two actions. If anything, in fact, it could be, the problem it can only be worse because, AMT work is usually, so AMT annotations are notoriously noisy. So we expected this issue to be even more relevant on crowdsourced annotation platforms. So when people disagree, when annotators disagree in labeling actions, we have inconsistencies within and across datasets. So I'm going to show now same action belonging to 3 different datasets. The action is take up, and we will see how the video clips were segmented differently. So for Bioid, this segment here, we see that the action is quite tight, and the clip contains only the motion involved in the action of taking the cup. For GTA Gaze Plus, we see that the segment is kind of loose because we can see that the person picks up the cup and carries it for a while. And finally, for CMU, the segment contains also the action of opening the cup, but prior to picking the cup up. And that is a different action, a different interaction altogether. So we see that, again, there are different ways of labeling the same action. And models are sensitive to such bounded variation. And this is because the visual content of a video segment delimiting the action in the video varies when the start and the end times vary, of course. So we wanted to evaluate this in a systematic way. So we took 3 different datasets and we altered the ground truth start and end times by generating new segments. These new segments had a new start and end time, which we made sure wasn't too far from the original ones. And we also made sure that each generated segment had a large overlap with the ground truth segment. So all of these generated segments are, say, plausible alternative of the ground truth segments, if you will. And what we did was we trained a variety of models, both old and newer ones, on 4 different datasets, on only the ground truth segments. And then we tested the models on both the ground truth and the generated segments. And what we saw was a drop in performance across all datasets for all models. So even i3D, which is quite a powerful model, also on more complex datasets like Epic Kitchens, which I'm going to talk about in a little while, exhibits a drop in performance when we evaluate the generated segment compared to the ground truth. And it's interesting to see that the generated segments, they look quite similar to the original ground truth. I'm going to show this in this video. On the left-hand side, you will see the ground truth clip, which was correctly predicted. And on the right-hand side, you will see 3 generated segments from the ground truth that look basically identical to us. However, they were predicted an incorrect class, and in most cases, the class is completely unrelated. So here we see take knife, and then we have closed fridge. It doesn't look like closed fridge to me. Turn off tap, and then we have put bowl. And again, you can see that the action segment, they look similar. And for another example, we have take bowl, the ground truth segments. We have pour oil, and finally turn on tap and turn off tap for the generated segment number 2 and 3. So in some cases, you could see why the classifier got the wrong answer, the wrong class, because there is some visual noise, like the tap is visible in the frame, but in most cases, there is no visual correlation between, at least any obvious visual correlation between the generated segments and their misclassification. So what we did was, okay, let's try to propose some guidelines to assist annotators. That means we try to sit down and think how we can precisely identify the start and the end time in a way that we can communicate to annotators so that they can be more consistent one with the other. We call this the Rubicon boundaries. And the Rubicon boundaries divides an action into 2 phases. The first one is the pre-actional phase, which contains the preliminary motion that is needed for an user to perform an action, and the actional phase, which is the action itself. So for example, for the action of cutting a pepper, the pre-actional phase in this case will be moving the knife towards the pepper, and then the actional phase will be the act of slicing the vegetable. We are going to see this in this video, because videos are better than images. So again, pre-actional phase, in this case, the preliminary motion is moving the knife towards the vegetable, and the actional phase is slicing the pepper, which is happening now. For the action of opening a door, in this case, sorry, opening a fridge, the pre-actional phase is the act of reaching out to grasp the handle, whereas the actual phase is the act of pulling the door open. We evaluated the Rubicon boundaries in two ways. We first first extracted the same annotators well, I don't want to say we used, but said that they helped us to label actions with the Rubicon boundaries. So basically, we told them, we gave them our guidelines, and we instructed them to label the start and the end time of the same action they labeled before. And they, in this case, we can see that because they were instructed in a more specific way, they could reach a higher level of agreement. We see this because the IOU not only varies less, but it's also higher on average for all actions. Again, we tried this on Amazon Mechanical Turk. However, it didn't really work for this kind of experiment because, well, we suspect that the problem with AMT is that annotators typically don't spend much time reading the guidelines, which I agree in this case were a bit complex, as in the Rubicon boundaries require some understanding of the task involved and require some active thinking. So we believe they may not be suitable for AMT because usually workers, they just click buttons. They don't spend much time reading the instructions carefully. So we don't see a good improvement for the IOU when using AMT and the Rubicon boundaries. We also re-annotated GTA GACE Plus, which was the largest dataset at the time, the largest egocentric dataset at the time, following our guidelines. And by just relabeling the dataset, we could observe a boost of about 4% top-line accuracy when evaluating this two-stream fusion network, which was the state-of-the-art back then for action recognition. And again, all hyperparameters and all the other settings were identical. So this boost is observed. Sorry, we observed this boost made only for the new labels, and I think this is quite remarkable that just precise labels can make such a difference. And maybe it sounds obvious now, but back then was kind of uncharted territories, and we wanted to work a little bit on this and see how annotation uncertainty relates to classification models. So now I'm going to talk about epic kitchens, which I hope you know already. Let me pause the video because it's a bit distracting. Okay, so I hope you know already epic kitchens, which is the largest egocentric dataset to date. We collected this video by simply giving 32 people a GoPro and asking them to film themselves in their kitchens at home for 3 days. They should start the recording as soon as they entered the kitchen and stop recording just before they were leaving it. You may ask why kitchens? Well, because it's in kitchens where we perform a lot of object interactions. That is where we can perform. We wanted to capture the largest number of actions possible. So the camera is mounted on the head with a strap. So we have an egocentric perspective, like this one in the video. And we collected 55 hours of footage, and we have about almost 40,000 action segments and 450,000 object bounded boxes. This was a team effort, so we'll just focus on the annotation pipeline, which is where I was directly involved. So annotating large video dataset is quite a big task. In fact, getting the video, especially now, is relatively easy. We can just pull videos automatically from YouTube and not label them, which is what some people do now, which is still valuable, of course. But if we want to publish some dataset that has good quality annotation, that's quite a different story. So we were trying to scale up the labeling pipeline. Because we have 50 hours of footage, we wanted to find a good compromise between the effort that it takes in labeling it and automation. So what we did, we asked our participants, the people who recorded the videos, to simply watch their videos after they recorded them and narrate their actions as they were watching the video. We call this a live commentary approach. They basically were watching the videos and then recording their voice with the phone. They were just talking over the video, and they could use any verb and nouns they could in this case. So we have free text labels, and then starting from, we pass these audio narrations to extract a timestamp that roughly locates the action in the video, and also to extract the text that was narrated. So we have a rough starting point, both for the semantic, for the class label from the narration, as well as the temporal location of the action. And then from these narrations, we obtain the action segments via AMT. We basically showed a window of the video around, centered around each timestamp to the Amazon Mechanical Turk workers. And we showed them the text that was associated with the timestamp. And we asked them to label the start and end times. Of course, each of these actions was labeled by multiple people, and then we try to find a robust way to integrate and all the various answers from the different workers, as well as reject noisy labels. And finally, we passed verb and nouns into predefined classes, so that we can train standard classifier with the clustered verbs. We also collected object bounding boxes. We did it only for the objects that were narrated. We call these active bounding boxes. And I'm going to show now an example of a full label video. I call this example because we can see how actions vary greatly in length. Like we have great carrot at the beginning, it's quite a long one. And then we have put down greater, which is very short. And also we can see how actions overlap, like pour water into saucepan and watch boiling water, etc. And we can see also the active bounding boxes for each frame. So you can see that there is quite a lot of actions. It's very densely annotated. That was our main purpose, to annotate actions densely. 2 years after we released Epic Kitchens, we worked on an extension which we call the Epic Kitchens 100. We call it 100 because we collected now, in total, Epic Kitchens now contains 100 hours of footage and around 90,000 action segments. Actually, we're releasing the dataset tomorrow, so and we are going to have a live webinar on Zoom and also on YouTube. So if you have some time, it will be streamed tomorrow, starting from 4 p.m. UK time or 5 p.m. Italian time. So for Epic Kitchens 100, we not only wanted to collect more videos, but we also wanted to improve our annotation pipeline at its core. In fact, while live commentaries was fast to start with, we had a few issues with this. Well, first of all, because the video and the audio tracks were not synced, as in the audio track was a separated track from the video. We have quite a large misalignment between narrations and video and the actual occurrence of the action in the video. And also because actions take place in a fast sequence most of the times, we have many missing actions. That's because while the narrator, while our participants were narrating the action, something was happening in the video, but they couldn't narrate. And for the same reason, we have rushed narrations. That means that people were trying to speak fast in order to catch up with the video. And that produced sometimes unclear video that was harder to pass later. So we wanted to avoid these issues, and we wanted denser and more precise annotations. So we designed an annotator tool, which we call the Narrator, which is also going to be released tomorrow. It's open source, so you can download it and play with it. So the Narrator is essentially a video player with audio recording functionalities. The main idea is that you play the video, and then when you watch, when you observe an action, you click the button, the record button, and you narrate the action again with your voice. However, now when you do that, when you narrate the action, the video is paused. And that means we no longer miss actions. That is like that is the trick of the narrator. Because we do that, we no longer miss actions, at least not as many as before. And also because we use this integrated interface, now narrations are perfectly synced with the video, and that makes the narration timestamp a stronger temporal cue, which will be helpful as we will see later. Also because the video is paused, there is no need to rush to speak. So narrations are clearer, and also the interface allows user to jump to a narration. You can listen to a narration, you can delete and redo every recording, so we can improve the quality of the overall result. This results in a great density of narration. Each of these tiny ticks on the slide is a narration, so you can see that they are quite dense and quite close one with the other. This is also because users could play the video at a slower playback speed, which, well, because the video is slower, of course, you can annotate actions more dense. The narrator increased our annotations density quite dramatically. In fact, before we had in the older Epic Kitchens, with the live commentary approach, we had on average about 90 actions per video, and now we have double that, more than 188 when we use the narrator. And also the percentage of the narration timestamp that was contained in the resulting action segment went from 50% in the case of live commentary approach to almost 80%. That's because the narrations are synced. And likewise, the action narration distance, that is the distance between the timestamp and the action narration, and the action segment when the timestamp is outside the bounds, went from 4.4 seconds to just under 1 second with the narrator. So how can we use the single timestamps? Well, we're going to see this now. So far, we've seen the annotated temporal boundaries is subjective. It's also an expensive task because it takes time and effort, and it's also quite boring, we have to say. So how can we label videos efficiently? So how about, instead of using a start and the end time, we use just one single timestamp that is roughly located around the action. And this idea actually came from the collection of Epic Kitchens, because we saw that we labeled videos by starting from narration timestamp. So I thought, can we use that single timestamp, which is quite rough, to supervise, to train an action classifier on such weak temporal cue? So when we have strong ground truth, we know when the action starts and ends, right? And that means that we can sample frames with confidence from the label bounds, and we can assign a class label to each of these sample frames. When we have only one timestamp, things are not quite easy because, well, first of all, because actions vary in length, and because usually the untrained videos contain many actions, and because the initial location of the timestamp is rough, so we don't have a guarantee that the corresponding frame is a good one. So what we did in this work was we replaced the unavailable boundaries with sampling distributions that were modeled by a plateau function that we see here. It's a very simple function. It's just a combination of two exponential. It's modeled by 3 parameters, which models, these parameters model the center, the width, and the slope, the steepness of the slope. And it can be, we decided to use this function because it's quite flexible. In fact, we can be, by tweaking the parameters, you can make it look like a gate function, like here, B, or even like a Gaussian somehow. Right, so what we do, we have given how our method works on untrained videos, and each of these videos is labeled with single timestamps with a class label. So what we did is we initialize a plateau by centered on each of these single timestamps. Now, because the timestamps are roughly located, and because actions again vary in length, this initial plateau might not be good enough. In fact, the plateau might be placed over background frames or could be placed over an irrelevant neighboring action, and the plateaus can overlap. So we don't want to do that. Ideally, we want to align these plateaus as much as possible with the actual occurrence of the action in the video. So what we do is we iteratively update the plateaus during training. So let's see how we do it. So to update a sample distribution, we first update the softmax scores of the classifier for each frame in the animation video. And we then generate update proposal. An update proposal is simply another plateau function that fits the softmax scores that fits the softmax score in a given video. The problem with that is, of course, there are different ways of fitting the plateau to the softmax scores, which are usually quite noisy. So, for example, here, this is might be a reasonable fit. We have a plateau that spans the two peaks. That means that the action is probably occurring throughout the two peaks. However, we can also produce something like this, where we have the plateau is narrower and is located over one peak. And likewise, we can also have this one, right? So which one is the best one? Well, we don't know that. And we need some way to find out. And because each of these plateaus is located over different frames, the content of the visual content of the video segments enclosed by these plateaus can change a lot, and that means that the videos may be more or less relevant to the classifier. So what we do is we rank these proposals. So here I'm showing the original sampling distribution that we initialized from the timestamp in green. And I'm also showing the softmax scores and the update proposal we saw earlier. So what we do is we calculate a confidence score, which is simply the average score of the frames enclosed by the plateau. And we do this for the sampling, for the initial plateau, as well as all the proposals. And what we do then is we look at the difference between the confidence score of each proposal and the original sample distribution, which we see here on the side. And the idea is if a proposal has a higher confidence score than the original sample distribution, that means that the classifier is predicting the action with more confidence outside the initial sampling distribution, and we update the sampling distribution accordingly. For instance, in this case, the blue proposal would be the highest one because that's the proposal that has the highest confidence score. Sorry. So this is an iterative process. It takes place while we train a classifier. And I'm going to show how this happens over training epochs. So here we have a single timestamp for the class OpenFridge and its corresponding initial plateau or sampling distribution. And we can see that the timestamp is not really well located. In fact, we don't really see the action of opening the fridge happening yet. As we saw earlier, the update is based on the softmax scores, which will be quite noisy at the beginning, of course. However, by assuming that we have other instances of the same class, either elsewhere on the same video or in other videos, and by assuming that overall the global location of the single timestamp is sufficient, for the class OpenFridge, the classifier starts to gain more confidence for frames that are closer to the actual occurrence of the action in the video, and we update the corresponding plateau based on this updated confidence, that is on the updated softmax scores. And we do this iteratively until the classifier reaches convergence. As you can see here at the last stage, the softmax scores are well aligned, are cleaner, and the final sampling distribution is well aligned with the action in the video. So it's time for some numbers now. I'm going to show some quantitative results. The baselines are obtained all with the same backbone CNN, which in this case is TSN with inception and batch normalization. we compare different levels of supervision. And this is what I'm showing here. Since this talk is about labeling actions, I wanted to show how different levels of temporal supervision affect the classifier. So the full baseline is simply the CNN trained with the ground truth start and end time. For TS and GT and TS, these are the timestamp baseline. For in the TS and GT case, the timestamp was sampled uniform from the ground truth segment. So it was simulated for all the three data sets. So this is a single timestamp is a bit stronger because, of course, it is contained, it is close to the action. And for the TS baseline, for epic kitchens, we use the narration timestamps, whereas for the other two datasets, because there are no single timestamps annotation, we simulated this timestamp by expanding the ground truth segment by 1 second on each side and by sampling 1 point from this expanded segment. So the timestamp can be outside, and in fact it is for the simulated timestamps as well. And finally, video label refers to untrimness, which uses video level supervision. That means there is no temporal supervision whatsoever. We just know that there is this action in the video, but we don't know where. This video level supervision has become quite popular because it's quite cheap to collect. And this is why we wanted to compare our supervision, which is stronger compared to video level labels, but still weaker to the full supervision. So it's kind of a compromise between annotation effort and performance. In the table, ACV stands for average classes per video. That is the number of distinct actions or classes that takes place in the video. And we can see that video level supervision with untrimness is remarkably quite good. It's quite sufficient when there are only one kind of an action in the video. So if I we see that on Thumos, which contains on average just one class per video, the performance of video level is remarkably high. It's very close to the full baseline. However, as the videos get more complex, as the average number of classes per video increases, we see that video level supervision is no longer sufficient. And in fact, the performance drops quite dramatically. This is top one classification accuracy. We see that instead with the single timestamps, we could still maintain a reachable performance compared to the full supervision. On Epic Kitchen, you will see that on the TS baseline, on the single timestamp, we are still quite behind. That is because the single timestamps we used in this case were the narration timestamps, and this work was done on the first edition of Epic Kitchens, where the audio and the video tracks were not synchronized at all. So these single stamps are quite rough, and this is well, we can see this from the poor performance that we see on the TS with the TS base. Some qualitative results. So here I'm showing the single timestamps for some parts of different videos with the dots, and we see that the dashed line is the initial sample distribution that we initialized from these timestamps. The horizontal bars are the ground truth segments that we use only for plotting, and finally we see that the dashed the dashed kind of washed out colors, solid lines represent the intermediate plateaus that were updated iteratively, and finally the solid one is the final distribution. And we can see how the method is able to find the right, converge towards the relevant location of the video, even when the initial location is poorly located. Like, for example, in the B example, we see that both actions, well, in the green case, we say that the initial timestamp is located over background. However, as we train a classifier, we could reach more relevant frames, and this happened also for C and F, etc. And the method is also able to work when actions overlap considerably, like in this case, J. And now I'm going to show an animation of these figures, as well as the visual content of the plateaus before and after. We will see how, we will see why the method updated the plateaus like in such in that way. So here is the first example. From the initial distribution, we regressed the right plateau. This is because at the beginning, for the action of cricket bowling, we see a person explaining how to throw the ball. That is not really relevant to classify. And in fact, after the update, we will see that this part of the video segment was removed. We see that the initial plateau is tighter, right? And the same happens for the action of cricket shot, where the updated version is shorter and contains only the frames that are relevant. And we can see this also because they align well with the ground truth, which again was used only for plotting. I'm also going to show another sample, which I quite like from Epic Kitchens, because we see how the method is also able to work when actions are very tight, when they occur one after the other, and when the initial plateaus overlap one with the other considerably. This is the example that is labeled here as J. So here's the animation. We see that even though there's a large overlap between wash spoon and wash fork, the method finally eventually regresses and separates the plateaus so that we can locate the actions in a better way. We can see this also with all the action clips before and after update. However, I think that the playback is a bit choppy on your side, so I'm afraid that you won't be able to see much. But this video is also on YouTube on my personal YouTube account. So if you are more interested, also about more details, I'm happy to give you the link, and in general, also happy to take any questions in a couple of minutes. In fact, I reached the conclusion of my talk, and to wrap it up, we saw that labeling actions is a subjective task, but it's also an important one. And this is because accurate annotations can make a difference. We saw this with the Rubicon boundaries when we relabel a large data set. We obtain a boost in performance just by having better temporal labels. However, robustness remains an open issue. This is because typically models are designed taking the ground truth segments for granted, right? They are designed to trust the supervision, and that means while we can reach more agreement with better annotation guidelines, we need to change the way we learn from noisy annotations. That means we need to move towards weak supervision, which leads to the final point of the conclusion, because given that datasets are growing increasingly larger, it's becoming really an increasingly harder task to label them accurately. So I like to end this presentation with, are precise temporal boundaries really viable and necessary? Well, I want to believe they are not. And I think that weak and self-supervision is the way forward. That is, in fact, what I'm currently working on during my postdoc. I'm still working on weak supervision to train action classifier from untrained videos. And I thank you very much for your attention, and I will be very happy to take any questions.
Thank you, Davide, for that excellent talk. First, I would ask those connecting on YouTube, if you have questions, please post them in the comments and we can direct them here. Meanwhile, starting with questions from the Zoom attendees, a question for the speaker. Remember to unmute your mic before asking the question.
Yes, I have one, but if okay, so it's actually on the first part in the graph semantic and
yes.
Okay.
I'm trying to get the slide. Yeah.
Yeah. Sure. So the point, my question is, I didn't get this network is it's built manually or it's something automated? Because I don't know if I have one question or two questions, so let's go with the first one.
No worries. So it is automatically built. That is the training part of the model. So we have these video clips that were encoded with some pre-trained features, and then we have web labels, and this is it's part of the algorithm. So we build this automatically.
Okay, and so I have a second question, and is this building process costly somehow? Because I don't know, I have general knowledge of graphs, and I get used to build graphs with some semantic senses. It could be quite expensive from a computational point of view, but so that's the question. Is this expensive for real, or?
It's not really expensive, especially, it's a good question. It's not really expensive, especially if you compare that to the training and the extraction process of the CNN. So building this, I honestly don't remember now how long it took, but we could run all our experiments on just normal desktop CPUs.
Okay,
so everything was done on the CPU. We didn't use a GPU for the graph.
Okay, perfect. Thank you.
No, thank you. Any other questions?
So I have a small curiosity. In the beginning, so in the single timestamp supervision, the
Yes.
overall, it changes the way the final boundaries, but how do you start with the initial ones? Maybe you already said it and I missed it.
So these are initialized from the single timestamp. So you can see this here, for example, or maybe you can see this better in the first slide. So this is an untrained video, and each of them is labeled with a single timestamp, which is associated with a class label, like this. And then we initialize the plateau by fixing the WNS parameters. So all the plateaus are identical at the beginning. What varies is the center of the plateau, which is the single timestamp itself. Does that answer your question?
Yes. And I have another one related to Epic 100. So what are the kind of questions that you're planning to deal with over and above the original Epic dataset that this particular one would be probably helpful with?
So there are two aspects. First of all, we have much more actions per video. So that allowed us to introduce more challenges. So usually in the previous editions, we had action recognition, object recognition, and action anticipation challenges. But now, because we have denser labels, we also have action localization challenge. And also because we have better single timestamps obtained with the narrator, we have also weakly supervised challenge. So by collecting these better labels, we hope to foster the community to undertake some difficult challenges, because again, our videos contain many different actions that are quite hard to train on them. It is quite hard to train on them. Another thing I didn't mention, because again, I didn't really work on semantic, is that we also improved the verb and noun clusters. So in fact, in the extension, we have, I don't think I have a slide for this, but we have fewer verb and noun clusters because we obtain a better clustering of the narrated text. That also improves the overall quality.
Thank you.
Thank you.
Any more questions?
I have a hi. I have a curiosity. I don't know to what part of the talk is actually related, but I have the feeling that with the latest individual instance annotation that you've been talking about in the last part of your talk, it could be related
Yes.
somehow. Do you have any interest in the anticipation of the action, or better, in recognizing the action as soon as possible? I suppose that this would be the type of thing I'd be interested to hear your opinion about.
Yeah, this is very relevant. In fact, this is called action anticipation, right? Where the task is given a window, a temporal window, say of 1 second. We try to predict the action that is happening in the future ahead, right? And I personally didn't work on this, but we had a challenge on this for the previous and also for the new version of the dataset. Actually, so Epic Kitchen was collected. It was a team effort between Bristol, Catania, and Toronto. And the guys in Catania, especially Dr. Antonino Furnari, he's currently working on, his main focus is action anticipation. And I think he published a paper, ICCB19, and recently now also TPAMI, exactly on this topic. So using Epic Kitchen. So if you are interested into that, I highly recommend checking out his work, because again, it was action anticipation specifically on Epic Kitchens.
Right.
I hope that answers your question.
Yeah, that's very interesting. I'll have a look. Thank you.
Thank you.
Yeah, sorry. I don't know. Maybe you can send through Gorvi the links to the
Sure.
presentation of the new data set, so that we can join, because it would be very interesting to us to have the
So,
details. Yeah.
I will. You can also see here at the top, but of course, it's not easy to.
Sorry, I didn't see. I didn't notice. No, that's fine.
There is a lot of text. So if you just Google Epic Kitchens, it should be the first result. This is the main web page dataset, and there is a link to register for the Zoom webinar.
Great, thank you.
It will also live stream on YouTube.
Are there any other questions? Okay, I don't see any also on the YouTube channel. So
okay,
let's wrap up. I would ask everybody to unmute their mics and join me in a round of applause.
Thank you. I think this is the first time I received a virtual round of applause. Thank you very much.